Okay, everyone, let's get started. There are 26 people here. Seems like our numbers are dwindling by the week, but I applaud everyone who has made it even this far. This is week 5, I think. No, this is week 6. It is week 6, actually. Yeah, so your 6th homework assignment will be due this Friday. So I applaud you. I was looking through the list of people who are here and looking at your grades. Everyone who is attending class is doing pretty well. Everyone is doing well on the in-class assignments. So you all are on very good track to doing very well on the math portion of the SAT and beyond. So Long says, all the weeks are blending into each other into one big math block. Yes, in fact, today we're going to begin by taking sort of making a little compendium of the course. And we're going to sort of look at this blob. I think blob is a good word to describe it. Hopefully, it's more like a drawer. If you think of math as, think of it as having different compartments. But the drawers of this cabinet have little holes in them, right? And there are ways to get from one drawer to the other. So Lily said when is the last day of class? That is the end of this month, July 31st. So we are well past the halfway mark, actually. And we only have 3 weeks of true content to cover for the SAT. The final week is going to be a few days of review and then a few days of what I think will be more geared to the juniors and seniors. And it'll be sort of more advanced topics, but something that'll help the juniors and seniors. So on the last 2 days of the course, I'm not going to require the 9th and 10th graders to attend, but I will require the juniors and seniors to attend. The 9th and 10th graders are more than welcome to attend if they want, but it might just, I have a feeling it's not going to be very useful to them. So the last day of content is the Thursday before, Thursday, the 23rd. The last day of the course is the 30th, actually, I should say. Technically the 31st, but we don't even meet on Fridays. So, okay, so everyone be prepared with paper, pens, pencils, because there is a little assignment today at the end of the lecture. I wanted to clarify something logistically, and that is regarding the scholarship money. So there's a distinction between prizes. So first of all, thanks for, I think, Alexis for asking me. He emailed me about this. There is a distinction between prizes and the scholarship. So the prizes, this is like my money, okay? Like I'm buying small little things for you all. This is not IntelliChoice money, so this is not like an official thing. But for those of you who are doing well on these in-class assignments, like the one you're going to take later today, there will be some form of a monetary award, and I think it's going to be in the form of a gift card. So maybe like 4 or 5 people will end up with this, whoever's been doing exceptionally well. And I'll be also looking at attendance quiz grades. So all of that is going to boil down to a gift card or several gift cards for people. This is in stark contrast to the scholarships. So the scholarships, this is the true, like this is what IntelliChoice, our organization that Dr. Lee is the president of, this is what IntelliChoice pays for. So the scholarships will be awarded when you complete the SAT and send a screenshot of your score to Dr. Lee. And I will send Dr. Lee's email address at the end of the count. So you have that, so you can send your score to him and then be reimbursed. And I think he'll send a check to your home address. We have your home address when you signed up for the course. And that amount is still kind of up in the air, but it will be at least like half the cost of the SAT. It'll be a significant amount of money.
Is that just for the juniors and seniors?
No, that's for everyone. That's a good question. That's for absolutely everyone. And to qualify for that, you have to pass the course. So that's why I've been nagging at everyone to, okay, turn in your homework and make a B-. Okay, you have to make at least a B- on the course in the entire. And so I know for 9th and 10th graders, it's harder to make a B- than it is for the juniors and seniors. And so there will be a slight maybe like 1 or 2 points, 1 or 2 point curve for the 9th and 10th graders, but I'm not intending for there to be a curve for the juniors and seniors.
Well, what if I don't take the SAT till my junior year, which is in 2 years?
We are encouraging everyone to take the SAT in August, actually. So if you complete this course, this information is fresh on your mind. And okay, so people are messaging in the chat. What if we don't take the SAT, like it's not required for our preferred university? I would still take it. I would still highly encourage taking it. It's still, I know some universities are starting to do away with it, which is actually not a bad thing, I think. But I still think it'll open your options a lot. And even if you're a 9th or 10th grader, I encourage doing it just so you have a score under your belt, you know, in case you get really tied up junior, senior year and you don't have time to take it, or even if you just want to sort of have a sense of where you are and where you need to go. Yeah, we're hoping that everyone takes it. And the scholarship will, we can only apply this scholarship, you know, in these coming months. That would be preferred if you not delay, okay? Because then it's like, if you send your score in 2 years and ask to be reimbursed, we don't really know if our course helped. We want to know if the material we're teaching is actually helping you. So then we can modify the course accordingly in future years and so on and so forth. So yes, please intend on taking it. That's actually the next thing I was going to tell you to do. If you haven't done so already, register for the SAT, preferably August 29th or September 26th. And I will be sending a link to the College Board site for those of you who are not familiar. Here it is. Let me go to the chat. Here's the link to, this is where all the date, I just sent it in the chat. So all the dates are written here. But we would like for everyone to register for either August 29th or September 26th. And also keep in mind that, you know, with the virus going on, the nature of the test is different, right? So you're almost being a unique part of history by taking the test, you know, during this pandemic. So anyway, okay, so if you haven't registered, register for preferably one of these 2 dates. So we're going to make a compendium of the course so far. So we've come a very long ways. And you all should be very proud of yourselves for getting this far and for doing the homework and going to the office hours. And really, I mean, you all have been treating this very seriously, and I appreciate it. So if we were to make a big sort of schematic of what math is, I would put everything that we've talked about in the realm of algebra. You know, this is, we've talked about lines, we've talked about parabolas, and we've talked about polynomials, and we've talked about exponentials and logs, and we've talked about how to transform these things using absolute value and inequalities. We've talked about, what else, am I missing anything? I mean, what else have we talked about? I think I hit everything. And last week, what did we talk about? Last week was it exponents and logs? I don't even remember. Look, that's how quickly this is escaping me. Okay, and then we also talked about one other topic that does not lie in the realm of algebra. That's kind of cool. See this program I'm using it. Anyway, we talked about one other topic, and that was dimensional analysis. And so that actually falls into this thing of physics, right? Math doesn't actually have dimensions. You know, in math, there are truly no dimensions. Dimensions come from nature and physical reality. And so physics provides this little thing into dimensional analysis. And so if you're thinking about math as a whole, physics is a branch of math. Physicists would say that math is a branch of physics. But anyway, and now we're also, in terms of sort of history, a true understanding of physics, a mathematical understanding of physics, was very late into the picture. And it was truly, Galileo was kind of the first person who really employed algebra in a very popular and concise way to explain physical reality. You might remember the videos, that they've recreated of Galileo rolling things down a ramp and then measuring the acceleration due to gravity by looking at how this thing accelerates. And he found that that its position increases quadratically. In other words, that there's a constant acceleration. But long before algebra and its application to physics, there were other ways of looking at the world that were much more intuitive and visual, actually. And these ancient forms of math, this is what we're going to be talking about for the next 2 weeks. So in a very real sense, I was talking to someone this morning who I hope is in the lecture today. One of our students is very interested in history, and I would imagine many of you are interested in history. And so you'll find that the next 2 weeks will be largely historical in nature. We're going to be thinking about the progression of how these things evolved and sort of culturally and in terms of popular historical figures. So it's very interesting. It's very much like a history class. So I hope that's interesting to you all. So before I tell you what these subjects are, I'd like to tell you where these two things led, just to get a full picture of what math is. These two things led to calculus. Physics and algebra led to this notion of calculus, this development of this field, which was really invented by Leibniz and Newton. And so those of you who are seniors, you're going to be studying these things that were discovered very relatively recently, like in the 17th century. So in the progression of math, calculus is very recent. And calculus in itself branches into many different fields of study. There's multivariable calculus and the calculus of variations and theoretical concepts of calculus. It's a full universe in itself, but calculus is the most recent, in a sense, addition to algebra and physics and math in general. So the ancient subjects, however, are trigonometry and geometry. And in fact, geometry predates trigonometry. And yet, I was actually speaking with our tutors yesterday. I had a little conference with them, with Anya and Patricia specifically. And I asked them, what should we cover this week? And this was yesterday, so you can tell I was still planning. I said, should we cover geometry first or should we cover trigonometry first? And Patricia said, well, Patricia studies history, actually, as some of you may know who are working with her. She said geometry came before trigonometry, so historically it would make sense to cover geometry before trigonometry. However, we know from geometry that the simplest figure, the simplest polygon is a triangle. And trigonometry is purely the study of triangles. It's not the study of squares. It's not the study of rectangles, of polyhedra. So yes, so Egypt would like to know your location. I don't know what this is a reference to. Anyway, so we're going to cover trigonometry first, and then next week we're going to get into geometry. And I hope that this knowledge of trigonometry will inform your knowledge of geometry. And also, in a very true sense, trigonometry is a merging of algebra and geometry. We will be solving trigonometric equations, which is much like solving algebraic equations, but with some spice. So with some geometric spice. And so in a sense, it's a very good way to introduce you to geometry. So this is sort of all of math. And you might remember from our very first lecture that we made a similar diagram. And you can now appreciate how much you've already seen. All of this stuff, including some calculus. We've talked about differential equations, and we've talked about this idea of derivatives. We've touched on some calculus. So you should be very proud of yourself. I mean, to me, this is the hard stuff. This is the stuff, geometry and trigonometry is the stuff that people have known for millennia. Okay, so people are talking about pyramids in the chat. So I urge those who are talking about pyramids in the chat to direct your energy, your positive energy, I think it is positive energy, to what we're doing here. So the next 2 weeks of the course, it's very different from what we've been talking about. It's going to be in a very real sense, a trip back in time. So can someone tell me when they look at this word, trigonometry, what are the two words that make up trigonometry?
Triangle geometry.
Say that again, Adi.
Triangle geometry.
That's good. Yeah. So actually, the Greek word for triangle is trigono. Okay. And sometimes you'll hear a triangle referred to as a trigon. So anyway, this means triangle, and geometry is actually not in the root of this word. Metry in general is the measurement, the study of measurement. So this is where we get the word meter from. You can think of this idea of measuring nature. So meter or metry. Geometry, the word geometry, the thing that we're going to be talking about next week, what is the root? So obviously this metry is still there, but what is this geo? What does this mean? Where does that word come from? This is almost like English class. Earth, yes. Very good, geo. And actually, if you are curious, for those of you who like history and Greek history specifically, the word geo comes from the word Gaia, which means Mother Earth. Gaia. Okay, little history for you, I guess, linguistics. So geo, geography, same thing. Yeah, so geography, geometry, they all share the same root. And it's very interesting because geometry is so fundamental to nature, and yet it's named after what we now know is to be a very small planet, a very, very small part of the universe. But to these ancient peoples, the Earth was sort of pinnacle of nature. So the early applications of trigonometry were the following fields. Geodesy. Does anyone know what this is? I would be curious. So it has the same root, geo, related to Earth. Any guesses? No one knows what geodesy is. So geodesy is the study of geodesics, and a geodesic is the shortest path on a surface, the shortest path between 2 points on a surface. So on a plane, the geodesic of a plane is a line. The shortest path between 2 points is a line. On a sphere, the geodesic of a sphere, I like how it's auto-correcting my shapes here. The shortest path, if you want to go from Dallas to Houston, say, you'd be traveling along a great arc. You'd be traveling along a circle, right, whose diameter, whose radius is the radius of the Earth. This is called a great arc. So geodesy is the study of such figures. And specifically in ancient, I urge you to read the Wikipedia page. It's very interesting. People were very interested in learning sort of the shape of the Earth and how the Earth precesses and how it rotates and how it orbits the sun. And the way they would study these things is they would erect big columns. So they would have a platform, and then they would put like a big column, and they would look at its shadow as the sun, through the seasons. And the sun's position moves, through the seasons, which is an apparent effect. It's really due to the tilt of the Earth. That's why the sun's position moves from month to month. But they would look at the shadow cast by the sun at different times and in different seasons. And there was a great astronomer named, I would like to just do this slight diversion on geodesy because it's very interesting. There was this great astronomer named Eratosthenes I think of Alexandria. He was Egyptian Greek kind of astronomer. Alexandria is now what the city of Cairo is. But Eratosthenes was a genius, and he actually, I think this was definitely BC days. I don't know how far into the BC days, how early he was, but he measured the circumference of the entire Earth using nothing more than a few sticks in the ground. And the way he did this was he was in Alexandria. So this is the Earth, right? He knew it was a circle, and he wanted to know how much it is, going across. He wanted to measure its circumference. And he planted a stick in Alexandria. And then there was a small town a few miles south of Alexandria. And he planted a stick there too. So I'm exaggerating a few miles here. This is significantly more than a few miles if this is to scale, right? So this is the Earth. And for those of you who are not familiar with astronomical notation, the Earth is often denoted by this plus sign. The sun is denoted by a dot, like that. Okay. And what Eratosthenes did is he noticed there was this, when he went to this place, he knew that on the summer solstice that there was a well. So he planted this stick. He planted it next to a well where on the summer solstice, so when the sun is right here, the sun, the rays of the sun penetrate the bottom of this well. They would go exactly, a well is very deep and it's very hard to get light to the bottom, but on the solstice and only on the solstice would the light reach the bottom. And he knew at the same time, he had clocks, I don't know which, probably sand-based clocks. He knew at the same time in Alexandria that there was a shadow. So here, there was no shadow. And he knew here that there was a shadow, and the shadow would have looked something like this, right? If the sun is here, it would have looked something like this. And so using the shadow, he measured what this angle was. Here there was no shadow, right? Here there was no shadow. Here there was a shadow. And by looking at how steep the shadow was, he used some basic trigonometry, and he found out what this angle is here. And he also knew this distance. So, I'll use different colors. He knew this distance as well. And we will soon learn that if you know the distance of an arc and you know its corresponding angle, that you can find the distance, in other words, the circumference of the entire corresponding circle. And Eratosthenes is his name, Leanne. Yeah, Eratosthenes. It's a fancy name, and if you want to impress people, you can say his name and tell them this story, because he was brilliant. And he measured the circumference of the Earth with, I think, like a very small error. I think there was an error of like 2%. Just amazing. A very simple experiment, but to measure something so big is truly, I think, a huge accomplishment. So this is sort of diversion on the field of geodesy, which is the study of Earth. Also, trigonometry is used in celestial mechanics. Celestial mechanics is the apparent motion of the planets and the stars and the moon and the sun across what is called the celestial sphere. And so just to give you an idea, here's the Earth. Here's we think, astronomers even to this day, think of the celestial sphere as an imaginary place. It's obviously the Earth is not the center of the universe, but it's very convenient to think of all stars and everything in the night sky as projections onto the sphere. So maybe the sun is here and Mercury is here. Obviously, these things don't exist on a sphere, and these things are not equidistant from Earth. But the field of celestial mechanics is based on the premise that everything is equidistant to Earth, and its goal is to model the motion of these planets and different objects, comets, the sun, the moon, using this system. And it becomes highly trigonometric in nature. And so celestial mechanics was a very popular field in antiquity. And lastly, navigation was a huge part of a huge application of trigonometry. Columbus was a fantastic navigator, and he had a great crew, and that's how he was so successful. So especially in the days of the imperial, sort of imperialist Europe, navigation was hugely, but navigation goes way back. So anyway, Adi mentioned that he thought it was mechanical engineering made by angels. So this is funny. So there's a great quote. So you can tell I'm very passionate about all of these things. And trigonometry is truly a beautiful thing. But I do want to say, Adi, you mentioned that there are angels. There's a great quote by Richard Feynman, who was one of the greatest physicists of the 20th century. And Richard Feynman said, he said, you may think, so beautiful Feynman, as always, beautiful. You know how planets go around, so here's the Earth, and here's the sun, right? And different planets go, I think this is the sign for Venus. That's not true. Anyway, different planets go around the sun at different rates, and people in early days thought that that there were angels. You might see diagrams that there were angels pushing the planets along. So here was the Earth. You know, these are the orbits I'm drawing, and people thought that there were little angels. Here's my bad little angel pushing the Earth along this way. And Richard Feynman famously said that for those of you who thought that the angels are pushing planets tangential to their orbits, in other words, in this direction, he said, those people are not far from the truth. It just turns out, Richard Feynman said, that those angels are pushing in a different direction. Their wings are pushing inward. And so what Richard Feynman was saying was that these angels are not pushing the Earth this way, they're pushing them this way. And those angels are in other words, the agent of gravity. Gravity is what keeps things, centripetal force is what keeps things traveling in circles. So beautiful Feynman. So Adi, you're not too far from the truth. Okay, modern applications of trigonometry. This is from Wikipedia, and I just found this amusing because you can see how widespread these fields are. Music theory, here's our field, geodesy, audio synthesis, architecture. You can read this, and you will find, I guarantee that maybe half of you, at least half of you, will end up in one of these fields. You will definitely, no matter what you do, these fields and beyond, this is just a short list, trigonometry will pervade your life. So this is why I said, what you are learning consists of the fabric of the world we live in. It's so fundamental to nature, and I'm sure what you all will do. So, okay, so any questions about, this is just an introduction. Any questions about any of these things? I hope this is somewhat interesting. So the beginning of the story. So those of you who like history, you're gonna love this. And bear in mind, I'm not a historian, although I also very much like history. I really do. I think Patricia should have done the lecture today. She studies history. Anyway, the beginning of the story is with the Sumerians and the Babylonians. And this is where Sumer is. It's modern day Iraq, southern Iraq. This used to be a very fertile area. Now it's sort of more desertish. It's still a good place for agriculture. But this is, I think in history they called this like the Fertile Crescent or something. You all probably, this is more fresh on your heads. Anyway, a very early civilization. And the Sumerians were the first ones who noticed that as the Earth goes around the sun, it takes roughly 365 days to do so. And they approximated the year to be 360 days. So they said that every day, if the Earth, if 1 year consists of 360 days, that means that every day the Earth is traveling 1/360th around this circle. So they said, in summary, all the way around the circle is 300. Okay, that was a bad drawing. Going from here back to this point, 365 days, and for the course of 1 day, so here's the Earth 1 day later, right? It moves this way. 1 day they define to be 1/360th of this circle, and they define this. So you know that the 3 lines means by definition. They define this to be 1 degree. So 1/360th around a circle is 1 degree. And so degrees, that's why we have 360 degrees in a circle. And degrees, for that reason, are convenient, and we sort of like to think about them and use them still, but they are very much an earthly, an anthropic, anthropic means, sorry, not anthropic, a human-like. They're a human-like invention. They're not, the use of degrees is not very fundamental to nature. It's very much a, based on Earth. If there were other beings in the universe, which is very likely, and those beings lived on planets that had an orbital period of something different than 360 days, which is very likely that it would take a different amount of time for them to go around the sun, they would have a different, sense of angle. And so it turns out that degrees are not a very universal way to measure things. And tomorrow we're going to talk about a much more general way to measure angles. So anyway, I would like for you to appreciate how they figured this out, because as a Sumerian, you have to imagine that you were standing on the horizon. You were standing here. Here's you, Sumerian, and you're looking at the sun setting. And say this was 3 days ago. Today's the 6th. Say you watch the sun set at, I don't know, 8 p.m. or something. I think that's 8:30. I think is when the sun has been setting. But say it was 8 p.m. I don't know. And you look at the sun setting tomorrow at the exact same time. As a Sumerian, you would be very careful. You would be taking notes and stuff, right? In clay tablets. That's how they used to write. And you would notice that the sun the day before, sorry, the day after, so 2 days ago, July 4th, you would notice that it was slightly higher in the sky at the same time. And on July 5th, yesterday, you would have, I'm exaggerating the effect here, but you would have noticed that the sun was yet higher. And July 6th, so on and so forth. So every day you would notice that the sun is moving back by a certain amount. And the amount by which the sun is moving back is 1 degree every day. And so that's how a Sumerian would have interpreted this. And a Sumerian would have noticed, this was not the interpretation that Sumerians had, that the earth is going around the sun. I don't think they knew this. But they knew that it takes the sun, to them it looked like the sun was going around the earth, every 360 days, or roughly 360 days. And so to them, the interpretation of the degree was not the amount by which the earth moves around the sun. It was the angular amount by which the sun moves around the earth. But you realize that these two things are visually equivalent, right? If you were on the sun, then you would see the earth moving by 1 degree. If you were on the earth, you'd see the sun by moving 1 degree. So it's just a matter of your reference frame. But this is how the Sumerians truly interpreted this phenomenon. So this amount, angular size, is 1 degree in the sky, which is, for those of you who are unfamiliar, in the sky, 1 degree, so the moon is about half a degree, the moon. So when you look at the moon, just think, okay, that's like half a degree of sky. The entire, from horizon to horizon, is 180 degrees. If you were to go from west all the way back around the celestial sphere, back to west, that's 360 degrees. So 1 degree is a little bit more, than the diameter, than the angular size of the moon. Okay. So we have this notion of angle, and I want to give you a sort of vocabulary to describe angle. Usually we use Greek letters, and for this course we're going to use the Greek letter theta. So get very used to writing theta. Sometimes people like to use phi, sometimes people like to use alpha, but for this course we're using theta. And that's what they use on the SAT as well. Okay, so this is some amount theta, and sometimes people will draw like a arc here to show, that it's a degree. That's an angular measurement. And so Hipparchus, there were two people who first started cataloging the different sort of trigonometric relations of these degrees. And those two people were Hipparchus of Samos, a Greek mathematician, famous for many other things. He was also a great astronomer, and Aryabhatta, who was a Indian astronomer and mathematician. And Aryabhatta made a famous table of trigonometric values. He took the sine, and we're going to talk about what the sine is in just a minute. He took the sine of values, and he made a famous table that I think has been historically cataloged. And today, in this activity that you're going to do, you're going to be making a similar table with only 9 values of the sine. I think maybe 12 values of the value of sine, cosine, tangent. But you'll be sort of retracing the work of Hipparchus and Aryabhatta. And so trigonometry is truly not just the study of triangles, but the study of right triangles. Right triangles form the basis of trigonometry. And we define certain relationships, and I think this will be reviewed to many of you. But if this is the angle theta, we define trigonometric relations to be the ratios of various sides to various other sides. So, for example, we call that the sine of theta, which is abbreviated by sin. This is not said sin, okay? You say sine when you read this. So sine is the word. The symbol is this, sin, sine. So say sine. The sine of theta, okay, the sine of this angle is defined to be b, the opposite leg, over c. So opposite over hypotenuse. Okay, the cosine is defined to be, can anyone tell me?
A over B.
Very good, A over B. Yeah, don't be shy, thanks for, and this is adjacent, this is the adjacent leg. I call this the opposite leg because it's the farthest from the angle. This is the adjacent leg. It's the one right next to the angle over the hypotenuse. By the way, I should have clarified. The hypotenuse is the longest leg, so to speak, of a right triangle. Okay, it's the one that's across the 90 degrees. I should have given some background. For those of you who don't know geometry, this means 90 degrees, and this means so the hypotenuse is the thing that is the leg that's across the 90-degree angle. Okay, so yeah, adjacent. The cosine is adjacent over hypotenuse. And does anyone know tangent? What is the tangent of theta in this figure?
B over A.
Sorry. Okay. Thanks for catching. The cosine is not A over B. I should have looked more carefully. It's A over C. Sorry, the hypotenuse is C. I misspoke. Thank you. The tangent is B over A. So the tangent is the opposite leg over the adjacent leg. So B over A, which is opposite over adjacent. And so for those of you who don't know how your peers are getting these so quickly, there is an easy way to remember this. And I have a feeling you've all seen this, but this mnemonic, Sohcahtoa, and this means sine, this means opposite over hypotenuse, cosine, adjacent over hypotenuse, tangent, opposite over adjacent. So this is a quick way to remember. And there will come a day when you don't need this. I think maybe junior or senior year, it'll just be immediate. So good. So we have this sort of understanding now. Okay. And now I would like to introduce you to two special right triangles. And these are two triangles that ancient people knew of very well. So say you were building a tent. Say you were an ancient Sumerian and you were building a tent, right? And you knew that this was a 90-degree angle. It was like these two things were perpendicular to each other, right? And you had equal length rods here holding up your tent. And you wanted to know how many people you could fit in here, right? So does everyone see the picture? It's sort of a tent that looks like this. I'll try to draw it in 3D. Okay, that wasn't great. But anyway, you see the shape of the tent. And so you want to know how many people you could fit in here to lie down and sleep, right? You want to maximize the number of people. So you would want to know what this is. And ancient people knew very well that when you had two lengths of one, so two of the same legs, right? These legs have the same measure, that the hypotenuse was the square root of 2. And Pythagoras, the great mathematician Pythagoras, would generalize this result into what would be called the Pythagorean Theorem. But we have not derived the Pythagorean Theorem. We will prove the Pythagorean Theorem very soon. In fact, next week. But for now, just know that these were the known relations between I guess this is the hypotenuse for a triangle that has legs of 1. And also know that the angles here, that this is 45 degrees and this is 45 degrees. So I would write this down because you will need this for your assignment. write down the angle and write down the each of the legs, 1, 1, square root of 2. And there was another famous special right triangle. And this was also, you can see, if you're building a tent or you're building a home, you wanted to see how big it is, how big the floor is, how this problem would come about. But this is also a very similar, so something of similar importance, right? A very fundamental relationship. If you have one leg being a measure of 1 and the other leg, the hypotenuse being 2, ancient people knew. Can anyone actually tell me what this is? Who knows?
60-30.
Yeah, so good. You know that this angle is 30 degrees. And can someone tell me what this leg is?
Square root 3.
Is this correct?
No, it's just square root 3.
Square root of 3? Yeah, I think you're right. Yeah, that's embarrassing. Okay, I've forgotten. I've confused my trigonometric values with my yeah. And so for those of you who want to check, the sine of 60 is root 3 over 2. Anyway, it's square root of 3. Thank you. So this is what ancient people knew. And so write both of these things down, okay? Because you'll need this for your quiz. So by the way, there is no quiz today, but in 4 minutes, you're about to be emailed this assignment. So just check your email in 4 minutes. But before we begin this activity, okay, has everyone written this down? So I would memorize these things for the SAT. I think they might be given like on the front cover of the test, but these are worth knowing. Okay, assuming everyone has written them down, let's practice identifying the various trigonometric relations given some angle theta. So someone tell me, what is the sine of theta in this drawing?
A over C.
A over C, very good. What is the cosine of theta? This should be very fast.
B over C.
B over C, that's adjacent over the hypotenuse. What is the tangent of theta?
A over B.
A over B, opposite over adjacent. Tangent of theta. Okay, great. I just want to give you all some practice with different triangles. How about, let's see, someone else. Tell me what the sine of alpha is here.
B over C.
B over C, very good. Opposite over hypotenuse. What is the cosine of alpha?
A over C.
A over C, because it's adjacent, the adjacent leg over the hypotenuse. And what is the tangent of alpha? Should be the opposite over adjacent.
B over A.
So don't think about the letters, think about the relationships of the sides. Because the letters might not correspond. Like I think, yeah, see here the A was the opposite leg. Here A was the adjacent leg. Oops. Yeah, here A was the adjacent leg. So anyway, so be very careful. Don't memorize letters, memorize the shapes. Can someone else tell me what the sine of gamma is? This is gamma, by the way. What is the sine of gamma? Opposite over hypotenuse is sine, and it's 40 over 41. So it can be a number, right? Your trigonometric values don't just have to be letters. They correspond to numbers. And what is the cosine of gamma? Someone tell me.
9 over 41.
Very good. And what is the tangent of gamma?
40 over 9.
40 over 9. Very good. Okay, so I think you all are catching on to this very well. So you should be very prepared for your activity, which is going to be sent out in a minute. Now, there is one question, a few questions at the end, where you're going to be asked to imagine extreme triangles. And you're probably wondering, what is an extreme triangle? Well, an extreme triangle, what you're going to be asked to do is to imagine that you have this triangle, and then you're going to shrink one of the legs down to nothingness. So A, in this case, is what I'm shrinking. And slowly, I can't draw this too well, but A, you'll keep shrinking A down to 0. And then you'll be taking sort of the trigonometric, you'll be taking sine, cosine, tangent of this angle here, or maybe of this angle. But anyway, this is what, and using this method of shrinking down, you're going to be able to find the sine of 0, the cosine of 0, the sine of, the tangent of 0, as well as the sine of 90, the cosine of 90. So, okay, so this is what I mean by shrinking it down. So at this point, the quiz should have been sent out. I had it scheduled to be sent out. So check your email. You should have received it. Let me know if you haven't. What I'll do is I'll also post it in our chat here. So if there are people who can't get to their email right now, it's coming right here. Okay, so I just sent it in the chat as well, if you can't get to your email. So I'll hang around here until 11, and then you all are to scan and submit your assignment to me at 11 a.m. And I'll keep this up for you all. Okay, you don't see it, but okay, so literally right above the message, just click on that. Right above the message. Oh wait, did it not? Should have sent. Is everyone else able to access what I just sent in the chat? Okay, Leon said it did send. So Biruk, were you able to see it now? Okay, what's your email? Here, okay. I'm literally just gonna, I just sent it again. Tell me if that worked. Click on that thing that I just sent.
Yeah, I don't see anything.
Are you in the chat?
Yeah.
Did you just see what I sent? It says trigonometry in class assignment. I sent it in the chat, in the group chat, where you're also messaging.
I don't see that in the chat.
You don't?
Yeah,
see,
same.
that is very strange. You pressed.
It's not in the chat.
That is bizarre. Okay, well, have you all checked your email?
No, it's definitely in the chat. Yeah, I just hit download from in the chat. It's 320
It's not-
kilobytes.
There's nothing in there, and there's nothing in the chat for me.
That's odd.
Okay, who is speaking? For those of you who don't see it in the chat, just check your email. It should have sent to your email as well. Nishan said, I think you sent it private. It says it's sent to everyone, but. Okay, so who has not received it? Yeah, so Leanne said, are we done with class? Yeah, you don't have to stay here if you don't want to. But yes, finish the assignment by 11 a.m. and then just scan and email it to me. Okay, so let's see. So Biruk, is it Aruhi? You also are not seeing it? Okay, you found it in your email. Good, okay. So I'll give you a few extra minutes because it took some time to find. Okay, but I'll stick around here for a few more minutes, and people need help. I can. Steve Brogan, can I just write the direct answers and send it to you? That's fine. Yep. Okay. See you, Leanne. Have a good day.
Wait, I'm confused on what we're supposed to be doing, like on the worksheet.
On the worksheet. Okay, so you see, are you looking at the worksheet right now?
Yes.
Okay, so let's see. So you're given these special right triangles, right?
Mm-hmm.
And you know, we know what the relations between the legs are. You know that the leg, if you look at the whiteboard, like what I'm sharing, you'll see these exact relations. And so you can fill these in onto the worksheet if you'd like. And so you
Okay.
know that the sine of 30 degrees is the ratio of the opposite leg to the hypotenuse. And the opposite
Mhm.
leg is, you can think of that as 1, and the hypotenuse is 2. And so what is the ratio between 1 and 2? Well, that's just 1/2. So the sine of 30 is 1/2.
Oh, so we're supposed to put in those numbers into the triangles.
Exactly.
Okay. I was really confused on what we're supposed to write.
Okay. But it sounds like you figured it out.